It's not an exaggeration to say that we are living at the historical moment. The historical moment may be different for different people. To me, the historical moment that we are living through this year is the 550th anniversary of the birth of Nicolaus Copernicus, greatest Polish scientist. And on this occasion, last weekend, Sunday, Monday, and Tuesday, there was a World Copernican Congress that took place in Toruń, which was historical in many respects. For one thing, a new Copernican Academy was formed, and we'll hear about it hopefully in a second. But also a number of very distinguished scientists came to the meeting, including 5 Nobel Prize laureates. And we are very lucky to have here 2 of them, Professor Barry Barish from Caltech University side, and Professor Art McDonald, who, as we all know, will be giving us talks and will tell us about the research that led to the awards that they've received, Nobel Prizes. But before we get there, let me very warmly welcome our distinguished guests, starting from the Minister of Science and Education, Mr. Murzek. And also Dr. Jakub Pietkiewicz, who is representing National Agency for Academic Exchange. We also have distinguished guests from outside, from abroad, Madame Ambassador Niki Kamba, from the Embassy of Greece, actually. Ambassador Nagma Mahmet Mulik from India, I think he's not here, but was supposed to be here. Madame Stéphanie Barlet from the Embassy of Canada. Monsieur Jean-Luc Schneider, the Attaché for Science and University Cooperation, welcome. And we're supposed to have also Mr. Guillaume Wegmüller from the University of Switzerland, but he couldn't come. Also, welcome to Mr. Nicolaus Jankowski from the Economic Diplomacy team of the United Kingdom Embassy in Poland. And I think this is it on the side of foreign representations. Now let me welcome the heads of the universities and institutes that have that are partners in this event, starting from Professor Adam Woźniak, the pro-rector of the Warsaw University of Technology. I think he's coming. I should mention here right away before I forget that the place that we are here, this beautiful auditorium, has been given us for this event for free, which should be appreciated. I welcome Professor Alojzy Nowak, the rector of Warsaw University, not here, and Professor Zygmunt Lalak, physicist, pro-rector of Warsaw University. Let me also welcome Professor Rafał Modelski from the Astronomical Center of Nicolaus Copernicus, Polish Academy of Sciences. I'm mentioning him because he's my director. And I should also very warmly welcome Professor Maciej Żylicz from the Foundation of Polish Science, and Dr. Jacek Orzeł, I don't know if he's here. He is from the National Center for Research and Development, director. Going down the list, we also have here a number of other directors. Director Roman Późniak from Institute for Physics, the Polish Academy of Sciences. Director Professor Adam Sawicki, Center of Theoretical Physics of the Polish Academy of Sciences. I understand Director Kurek could not come, but National Center for Nuclear Research is represented by Professor Eva Rondio, Science Director. And we also welcome Professor Wojciech Satua from the Department of Physics, the pro head. And I should also welcome Professor Marek Sarna, chairman of the Polish Astronomical Society, and Professor Bogdan Kowalski, who is the Secretary General of the Polish Physical Society. The chairwoman of the Physical Society couldn't come. She is somewhere traveling, I'm told. Let me also, I think by now I've covered the official list. So let me just basically welcome now our guest physicists from abroad who come here to the Congress and are also here with us, starting from Professor Michel Spira, who is the director of the Year of Basic Science for Sustainable Development. Very warm welcome. We're happy to have you here. Professor Antoine Kouchner, the director of Laboratoire Astroparticle and Cosmology, which is the institute which is our strategic partner in our project. And Professor Richard Bond from Canada, CETA. And Ms. Kinga Słomińska from the Foundation for Polish Science, who is our... Sorry? He's on my list. He's on my list. Kinga Słomińska is Deputy Director of the Department for International Programs, and she is our guardian angel in many respects. Welcome to the directors, the heads of other international research agendas. Those who could make it, very warm welcome. I'm very happy to have you here. I think it's very important for us to be here together so that we can re-establish contacts after this terrible long night of COVID lockdown. So I'm very happy to have you here. Professor Dorota Pawlak, Professor Paweł Chorodecki, Professor Agnieszka Hacińska, Professor Vignesh Kumaravel, and Dr. Jakub Miecznikowski, I believe. And last but not least, let me welcome also Professor Cristiano Galbiati from the, Cristiano, can you show up yourself, who is a member of the International Scientific Committee, as well as Antoine Kouchner of AstroCeNT, and both are very strong supporters of the project. Apologies if I've missed somebody, but we've such an incredibly intense period in time in Toruń that I left all the organization to my wonderful staff. So all the blame goes on me because I just decided that they can do it by themselves, and I'm sure they will. They have. So without much ado, let me just ask Minister Murzek, Panie Ministrze, for just a few words of welcome in Polish.
Szanowni Państwo, była ta część budząca podziw, jak pan profesor opanował te wszystkie tytuły i osoby wymienione. Już bez tłumaczenia też, żeby był ten akcent, że jesteśmy w Warszawie, w Polsce, to też w naszym ojczystym języku dwa słowa. Rzeczywiście chciałbym zwrócić uwagę, że jest to moment historyczny, a nawet dni historyczne, ponieważ od kilku dni gościmy bardzo zacne osoby w Polsce ze świata nauki. Dzieją się duże wydarzenia. Mieliśmy kongres kopernikański, powołanie Akademii Kopernikańskiej, dyskusje między elitą finansów, dyskusje między elitą nauki, patrząc też na naszych gości, laureatów Nagrody Nobla. Myślę, że to też pokazuje w jakiejś tam cząsteczce ogromne aspiracje Polski, żeby we wszystkich wymiarach, w tym wymiarze naukowym, być w czołówce światowej. Dzieje się dużo i ten wymiar międzynarodowy jest ważny. Wczoraj słyszeliśmy z ust prezydenta Stanów Zjednoczonych o tej wyjątkowej roli i misji Polski. Mówiliśmy o ogromnym wysiłku międzynarodowym, żeby przeciwstawiać się tej katastrofie, jaką jest wojna na Ukrainie. I dzisiejsza obecność pokazuje, że cywilizacyjnie tutaj jest sens łączenia sił, bo można i trzeba łączyć te siły militarne, żeby zwalczać to zło, które zaistniało, ale jakże piękniejsze i bardziej ludzkie jest łączenie sił w obszarze nauki, w docieraniu do prawdy, we wspólnych badaniach naukowych. Myślę, że te dni będą też jakimś wkładem właśnie w takie patrzenie i w przyszłość, i do góry, bo będzie o kosmosie trochę więcej, żeby rzeczywiście te wyzwania koncentrowały naszą uwagę. Dobrych rozmów, dobrego spotkania, dobrych też kontaktów, które niech owocują jak najlepszymi osiągnięciami na miarę cywilizacji XXI wieku. Dziękuję bardzo.
Thank you very much, Mr. Budzek. Let me also ask our director, Professor Rafał Moderski, for a few words of welcome.
Since we are a little bit late, I will take only several seconds. I would like to welcome our distinguished guests. This is really an honor for me to have you here, and I also would like to welcome all of you. This is very good that there is such an interest in such a topic like science. And I'm very honored and very glad that AstroCeNT, which is a part of Nicolaus Copernicus Astronomical Center, has developed in such a way that we are able to guest such nice persons and such honored people here. I hope that this will be not the last time we have you here. You are always welcome, and I think that we will always try to organize such an event that we can fully enjoy presence of such a distinguished guest. So let's enjoy without further delay our scientific feast. Thank you.
Dziękuję, Rafale. Thank you very much. Just one quick update. The Warsaw University of Technology, Politechnika Warszawska, is represented by Professor Karpiesz, a prorector, who is coming instead of Professor Woźniak. You can just please say a few words.
Good afternoon, everybody. I just very shortly welcome to Polytechnic, Warsaw University of Technology. It is great honor for us that we can be a host of such very prestigious event. So I don't want to speak because I want to see and hear what's our guest, our professor want to say. So, welcome to our university.
Thank you very much. All right, so we're only 5 minutes behind the schedule, so it's not too bad. It's not too bad at all. The plan for the rest of the meeting is that we'll hear 2 speeches, first by Professor Art McDonald, and then by Professor Barry Barish, and that will be followed by a question and answer session. So I hope you will enjoy both the talks and also the discussion that will follow. Let me introduce the first speaker, Professor Art McDonald. Currently holds the Gray Chair Emeritus position. He was born in Sydney, Nova Scotia in Canada. He has degrees in physics from Dalhousie University, both bachelor's and master's, and from Caltech, where he did his PhD. And he has honored degrees from 15 universities. From 1969 until 1982, he was a research officer at Chalk River Laboratories. From 82 until 89, he was a professor at Princeton University. From 1989 until 2013, he was a professor at Queen's University. In other words, he moved back to Canada from Princeton. Queen's University at Kingston, Canada. From 2006 until 2013, he was Gray Chair. Chair means professorship in the British system in particle astrophysics, and since 2013 he's retired and holds the position of Gray Chair Emeritus. Now, since 1989 he has been director of the Sudbury Neutrino Observatory, SNO, as it is known, scientific collaboration. Among many awards, he is a companion of the Order of Canada, a co-recipient of the 2019 Nobel Prize in Physics and 2007 Benjamin Franklin Medal, the 2016 Breakthrough Prize in Fundamental Physics, and the 2013 Cocconi Prize of the European Physical Society, along with the SNO collaboration. He's a member of the Royal Societies of Canada and the United Kingdom, Foreign Associate of the United States National Academy of Science, and a Fellow of the American Physical Society. He continues to be active in basic research in neutrinos and dark matter, and I testify to it fully. In 2020-21, he was a Canadian lead on the project that has delivered more than 7,000 low-cost ventilators for the COVID-19 pandemic, along with Cristiano Garbiati, who will be hosting the question and answer session, moderating. It was a fantastic achievement in itself, and I'm sure it will be mentioned also in the talks. Professor McDonald is visiting AstroCeNT for the second time. I'm sure many of you remember that. He came here in 2019, and we were hoping he would visit us again soon. We know that this soon got a bit longer than we were hoping. Many of us were here in May 2019 when he gave a keynote speech. Despite the intervening period of lockdown, and actually also because of COVID, he has been in intense cooperation with me and with the researchers at AstroCeNT. And I hope he will explain what I mean here. Art McDonald and Barry Barish are on their way back from the World Copernican Congress, as I mentioned, held in Toruń last few days. And what else can I say? I think it's time to just welcome Professor McDonald to the stage. Welcome, Art.
Thank you. That microphone or that one? This one. Great. Well, it's a real pleasure and an honor to be here. And I also greatly appreciated the opportunity to attend the Congress in Toruń, honoring my friend Nicolaus, my friend that I have learned a lot about in the last few days. And it's an honor to be associated with him and to be a member of the Copernican Academy going forward. Indeed, what we're going to talk about today is, in a sense, a modern revolution in our understanding of the heavens. What Copernicus brought to us was a new perspective on how the Earth is in relation to the Sun. The new perspective that has been obtained in the last 50 years or so, led in a large part by our friend and colleague Jim Peebles, who was with us in Toruń, is a new perspective on how the universe has evolved since the Big Bang about 13.5 billion years ago. And what I'm going to talk about today is experiments that we are involved in with AstroCeNT that take place in locations such as you can see at the top of the slide, where in all cases the detector for the process we're looking for takes place underground, and that is to avoid the cosmic rays that bombard our atmosphere, high energy particles that otherwise would make our detectors glow like what we call in Canada the Northern Lights. I'm not sure. Can you see Northern Lights in Poland? No. Perhaps you have to go to Sweden to see them. I should have a picture. The sky glows at night, and our detectors would glow if we were not shielded by, in the case of the Snow Lab in Sudbury, by 2 kilometers of rock above us. Because in the experiment, one of the experiments I'm going to talk about, the one that started our activity in this field, the Sudbury Neutrino Observatory, which is shown here on the side of the Snow Lab, we were detecting neutrinos from the sun 1 hour after shielding out a wide array of cosmic interactions that would have made our detector glow. The other experiments I'm going to talk about, ones that at Gran Sasso and in Japan that AstroCeNT is actively involved in, also take place underground for similar reasons. And in the case of Gran Sasso, we're looking for dark matter particles. In the case of the Hyper-K experiment in Japan, the objective is to determine properties of neutrinos that are at present unknown, but properties that could have a very significant role in the way in which the universe has evolved since the Big Bang, as I'll discuss in a moment. The point I wanted to make with this particular slide is that our universe is immense. You can see the scales listed up there. The largest scales are greater than 10 to the 24th meters, but they also range all the way down to the smallest particles, neutrinos at 10 to the minus 18 meters or so. We're in the middle in our solar system, observing this universe. But with these underground laboratories, we can observe things that are very relevant to all scales of our universe. By studying neutrinos from the sun, for example, we were able to understand properties of neutrinos themselves at the smallest scales. By studying dark matter, we're studying what influences the formation of galaxies and in particular, even our own galaxy, the Milky Way galaxy, because dark matter influences substantially the form, that beautiful spiral shape that you see there for our galaxy. It also influences many things in the process of evolution. since the Big Bang. We can even study neutrinos from the Earth with our detectors. We're studying uranium and thorium content in the Earth, and it turns out about half of the heat flow from the Earth comes from these elements, and we can study 600 kilometers down into the Earth with our detectors of neutrinos, and so we're doing geophysics, really, with those measurements. So you're probably not familiar with neutrinos unless you are a scientist yourself. They're very unusual particles. The protons and neutrons inside the nucleus of an atom that you will have learned about in school, surrounded by electrons forming the chemical composition of the atom. Those quarks and the electrons and the neutrinos are the particles we don't know how to subdivide any further. But the neutrinos are the most unusual of them because they don't feel the strong interaction that binds things inside a neutron, a proton, or even inside the nucleus. They don't have an electric charge, therefore they don't behave like the electrons you have flowing in the wires in your house. They only feel the weakest of all the forces, the weak interaction, and so they can travel through an amount of lead corresponding to the distance that light travels in a year and only have a 50% chance of hitting anything because they don't stop unless they hit the nucleus of an atom head on or the electron going around it. And so they're very unusual particles. Let's see if this works. That doesn't. Let me try on here. There. Very unusual particles. They come in 3 flavors, as we call them, although we can't taste them. That's a term that's fun to use. They are very difficult to detect because of this weak interaction, which is very valuable if you're trying to get them out of the sun. They're generated in enormous numbers in the nuclear reactions that power the sun. They are going through your body right now. If you hold out your thumbnail, in a second you'll have, of the type we were detecting, about 5 million go through your thumbnail, but you'll never observe it. In your lifetime, perhaps 1 neutrino will stop in your body and change 1 atom into something else and maybe produce a burst of light. But unless you happen to, unless your eyes happen to be closed and it hits you in the eye, many eyes are often quite closed by the time I get to this point in my talk. But anyway, unless you happen to have your eyes closed and it hits you in the eye, you're not going to even notice that one time in your lifetime. They really are rare and difficult to understand, and therefore it wasn't understood whether they even had a finite mass or whether they always traveled at the speed of light, having no mass as photons of light do. We were able to observe a process where they change from one of the flavors into others, which is caused by a finite mass, and therefore we and the Super Kamiokande detector in Japan were able to show in the experiments for which we were awarded the Nobel Prize this oscillation process that implies that they have a mass. In addition to that, since we were studying the neutrinos that come from the core of the sun by what are referred to as fusion reactions, that is light nuclei like deuterium and others in a chain of reactions that generate the light elements, including carbon, nitrogen, and oxygen that are such a large part of human life. They are generated in stars like the sun. So understanding that process of the burning of the sun is very valuable from a basic science point of view, but it's also valuable in the sense that the calculations that are done in this billions of degrees of temperature in the core of the sun, where everything's held in place by gravity, are also similar to the sort of calculations that you have to do in order to build a fusion reactor, where you're using magnetic fields to produce a bottle where the particles can't touch the walls or else they would melt them. So in terms of that technology on Earth, we have a full-scale test which is relevant to the calculations done there. And so very often it is the case that when you do basic science, you end up influencing applied science and things of benefit to mankind. Time magazine chose Albert Einstein as the person of the 20th century, not because he invented the laser or the computer or the GPS system, but because the things he discovered in basic physics are the things that enabled all those processes to take place and the enormous technological revolution that occurred in the 20th century. The Super Kamiokande experiment observed neutrinos which are produced in the atmosphere change as they traverse the Earth. And neutrinos figure in the theory of cosmology, which is here in a simple form. The idea is that on the left, you can see that about 13.5 billion years ago, it says 15 on here, but we now think it's more like 13.5, there was an enormous explosion and an enormous inflation of the particles that existed at that time that were being created out of energy, forming, we think, similar numbers of matter particles and antimatter particles that are the equivalent particle, but with just the opposite properties, such that when the two of them come together, you have an annihilation, as it is said. So, for example, in positron emission tomography, a very valuable medical process that is used extensively today, you inject a radioactivity into someone's veins, which then gets to the place you're trying to study, such as looking for a brain tumor. And when those positrons decay from that radioactive decay and find an electron in the person's body, they generate energy. They generate two back-to-back gamma rays that are easy to detect, and you then just connect the lines, basically, to find where the activity has gotten to, or perhaps where it hasn't gotten to because of the tumor. So in that case, you're using it in the direction where you have a particle and an antiparticle, which is coming together, which are coming together and producing energy. In this case, we think that in the Big Bang, energy was used to produce particles and antiparticles in pairs. And as I'll say in a minute, a big puzzle today is, where is all the antimatter? We only find it in radioactive materials. And that's one of the questions we're trying to address with our future experiments. But as the universe expands following the Big Bang, you see that it cools off as it expands. You find that by, as it says here, 10 to the minus 6 seconds, you can have the quarks coming together to form protons and neutrons. After 3 minutes, they form into the nuclei of atoms. And after 300,000 years, they form neutral atoms because the electrons attach. And at that point, it becomes transparent for the first time. It was a plasma prior to that. Light didn't get out. But there's tremendous information has been obtained by looking at the light that is left over from that period around 300,000 years after the Big Bang. That's still 13 billion years ago, but by this point it has cooled off to just above 3 degrees above absolute zero, about minus almost 300 degrees below zero in Celsius. Following the formation of atoms, they come together with even small perturbations, allowing gravity to form larger structures, galaxies, stars, and that happens around 1 billion years after the Big Bang. And then it continues as the structure is formed to the forms we see today. So let's talk for a moment about that first question, matter-antimatter asymmetry. Why is it that all of the matter dominates today? And the most accepted theory involves neutrino properties, partners at very high mass to the massive but very small mass neutrinos we observe that end up enabling a transition such that the antimatter has decayed away preferentially, leaving us with matter-dominated universe. And the experiments that are being used to address that question are, for example, there are several experiments in each category, but for example, the one that I'm involved in is a repurposing of the snow experiment to remove what had been heavy water in the central region and replace it with a light-emitting so-called scintillator with tellurium added. Tellurium is one of unusual elements that can give out not just a single beta decay, which is usually an electron and a neutrino, but instead 2 electrons and 2 neutrinos in some cases, or if the neutrino has properties that enable it to basically behave both like a particle and an antiparticle, then they can annihilate each other inside the nucleus and never be emitted, in which case you have simply monoenergetic, if you sum together the energy of the electrons, you have a monoenergetic process. And you can determine by studying this very, very accurately, and to do it you have to study a lifetime of about 10 to the 26th years, which sounds impossible, but if you remember from school Avogadro's number in a molecular weight of material, you've got almost 10 to the 24th particles. If you have tons of material, then you've got enough material that you can get up to more than 10 to the 26 atoms of material that could potentially decay, and then you just have to wait for a few years to make a measurement at that sort of level of sensitivity. It can also tell us the absolute mass of neutrinos, because these oscillation experiments only tell us differences. That's one part of what happened in the early universe with respect to matter-antimatter asymmetry. Another part of it is being addressed by the Hyper-Kamiokande experiment in Japan, which is about 10 times bigger than the original Super Kamiokande experiment, where muon neutrinos and muon antineutrinos are being shot across Japan by an accelerator near Tokyo. And making that comparison can determine the property of which ends up being representative of the difference between how neutrinos and antineutrinos behave. Antimatter asymmetry would be evident with these lighter neutrinos. And so that's a very major experiment happening in Japan. There's another very major experiment happening at Fermilab called DUNE. And AstroCeNT is very actively involved in Hyper-Kamiokande, as you can see from this slide, where the items with stars on them are the electronic elements of a very complex system. And you can see they're central elements in terms of the success of the project. So it's not a minor participation that AstroCeNT in consortium with the other institutions mentioned on this slide that they are participating in. But this other question of dark matter is a very major one, and we think that dark matter makes up on the order of 5 times as much mass as the mass of the glowing matter, which of course is the same matter that we are composed of. If you look out on a starry night, there's as much matter, in fact 5 times as much mass in the matter in the dark spaces as there is in the glowing stars. And there's an enormous amount of information that has gone into our understanding of this. And I'll just mention in a very superficial perspective a few of them that makes us think that dark matter actually exists based on its gravitational effects. We want to try to observe it directly, and so the experiments are very similar to the ones that I described for neutrinos, where you go underground, try to get rid of cosmic rays and are very careful about radioactivity in your experiment, so you don't get anything that obscures the dark matter signals. But the reason why we want to look at them directly is, in fact, the enormous progress that has been made in astrophysical measurements in recent years, and one of them called the cosmic background radiation, of which Professor Bond, my colleague from Canada, is, you can call him one of the deans of the field. He's been involved in it for many years and made tremendous contributions. What is seen when you study that light from over 13 billion years ago is a pattern on the sky which is very minor in its variation. Variation is only about part in 10 to the fifth. But if you ask what's the amount, if you like, the density of the light that is coming on various scales, in this case they're indicated by polynomials, but basically the vertical height in that plot is the power density, and the horizontal is a scale size, if you like, of those spots you see on the plot on the left. And what you see, and maybe you can't see, the red points are kind of summary points of some little blue dots that are the actual data point. But what's absolutely remarkable is that blue line that goes through the points, that's not just a line drawn through the points, that's a theory. There's a theory for that light obtained from over 13 billion years ago, which has 6 parameters in it only, and fits it to that degree. And it includes parameters such as the amount of dark matter. And in fact, whereas that first peak is influenced mainly by the ordinary matter, there are parts of that curve fitting that require dark matter to be involved in the equation. And I think that third peak is one of the areas where it's most strongly affecting things. These experiments and their interpretation are really very remarkable. I remember sitting at a seminar presented by Professor Bond in 1980, in which the data was a few points over this curve, generally obtained by flying balloons in cold latitudes and on clear winter nights. Sure enough, as time went on, and we got to do it in satellites, and satellites are another place where tremendous progress has been made. Going underground and going above the Earth to avoid the twinkle of the atmosphere has been a real advantage in terms of astronomy. But there are other things that are even closer to home, and that is, that's something that looks like our Milky Way galaxy. We can't get outside and take a side-on picture like that. If you look out on a starry night, you'll see a band of stars that are referred to as the Milky Way. That's because you're looking along the axis of the pancake sideways. But other galaxies, very similar to ours, look like that spiral form. And if you measure, as is plotted on the right, the velocities of the stars as a function of the radius, you get those black points. Now, if you simply have the gravity that's holding those stars in the orbits be what is observable in the glowing matter, you can imagine swinging a bucket of water over your head, and the tension in the string is the gravity that's pulling it in. There isn't enough gravity in just the glowing matter to explain the way in which these stars are behaving. You need 5 times as much mass holding them into that pattern, which is what's referred to as dark matter. It's also observed in the same sort of way, 5 times as much as the glowing mass, when you use Einstein's general relativity to do gravitational lensing on far distant galaxies, where you have, as you see the lower left, you have images of stars distorted by the lensing effect of the intervening dark matter. And so strong correspondence between the two ways of measuring it. And there's another one which is sort of a one of a kind as far as I know as a non-astronomer these days, but a kind of a pretty one as they presented it, and that is two colliding galaxies where the red data is taken from X-rays, which is the way in which the matter emits light, and the blue there is inferred from gravitational lensing, and you can see that they've already passed through each other, and the blue, the dark matter content has gotten through very easily, indicating that dark matter is not strongly interacting. And so weakly interacting massive particles are what appears to be needed, or at least one example of what appears to be needed for dark matter. So physicists love whimsy in their names for things, so we're a bunch of geeks looking for wimps when we're doing this sort of experiment. Another way to describe dark matter is axion particles, and that's another whole area of research which is being pursued extensively. So we end up, when you put a lot of things together, with a picture where dark matter is about 5 times as much as matter, but matter is only about 4% of the total of the mass energy density in the universe. This dark energy was observed by studying supernova at very far distances and finding that they've accelerated more than you expected. And so the gravity that you were taught in school, which was always attractive between two masses, needs a small repulsive force as well, which is referred to as dark energy or as Einstein's cosmological constant. Dark matter could be these weakly interactive massive particles, and that's what we're trying to detect by having them hit our detector in these underground locations. Now at CERN, with the highest energies available on Earth, they are attempting to produce dark matter for the first time since the Big Bang on Earth. The idea is that you, up till now, may not have had enough energy in your collisions to produce the mass of a dark matter particle. And so really what we're doing is very complementary to the sort of thing that's being done at CERN. What we try to do is to take advantage of the fact that we are moving through our galaxy where we know there is dark matter based on those rotation curves. There's also the movement of the Earth around the sun. And so we look for signals in our various experiments where the dark matter particle has scattered off a nucleus. Argon, liquid argon, in the case of the measurements we're working on with AstroCeNT colleagues, has some very wonderful properties that enable you to distinguish a recoiling nucleus from other forms of radioactivity, because that recoiling nucleus, indicative of a WIMP, gives a short burst of light, like about 7 nanoseconds, 10 to the minus 9 seconds, whereas the light from radioactivity is typically emitted over about 1.5 microseconds, or 10 to the minus 6 seconds. And so we can throw away millions of pulses from radioactivity and just look for those very few pulses from dark matter. We've been able to discriminate against radioactivity by factors greater than 10 to the 8th in the experiments we've done so far. Now, taking one lab as an example, this is Snow Lab in Canada. What you'll notice is that there's a number of different experiments. The one that is the precursor to the dark side experiment we're collaborating with people at AstroCeNT on, and people from AstroCeNT are also collaborating on the DEEP experiment, uses argon. There's another experiment that uses helium with a different technique. There's one that uses fluorine, neat technique where the dark matter particles produce bubbles and radioactivity does not. Another one here that uses silicon and germanium, and one that uses different techniques for using silicon. This is an example of an underground laboratory in Canada which was built by the Canadian government, and the argument was that if we build something like this, then the world will come and work with Canadians I understand that there is an opportunity perhaps in Poland to build an underground laboratory, and I can simply tell you that this has been a real success story in Canada. The experiment there stated to be Super CDMS. It's a $35 million US experiment that has decided to be sited in SNOLAB, and all of the accompanying economic spin-off of the construction of it and so on is, a lot of it is happening locally, but it also gives Canadian scientists an opportunity to work at the forefront of fields. And so an underground laboratory really for us has turned out to be a big success story. This is one of the deepest in the world, and in the laboratory itself we have ultra clean conditions. Everybody who comes down takes a shower and changes into lint-free clothing, which didn't work when we hosted Stephen Hawking. We had him visit twice, in this case in 2012, just a year before he passed away. But he was adamant. He had just recovered from pneumonia, actually, earlier that year. But he was adamant he wanted to see this. He'd been there for our opening back in 1998. The spirit of that gentleman is absolutely amazing. Composing word by word questions to our grad students underground. In his case, we vacuumed him off above ground, and there was a special rail car that took him underground. But he's really an inspiration, particularly when you know that essentially all of his work was done after he got the disability of ALS. So anyway, you can see the cleanliness of a remaining large space in our laboratory. This is the DEEP experiment and what it looks like. DEEP has combined with several other international experiments to form an international collaboration, 100 institutions, 13 countries, one of them being Poland, to build a sequence of experiments. First, dark side 20K in Italy, where 100 tons of argon is used with 20 tons in the central region, leading, we hope, in the longer term to an even larger experiment that could occur at SNOLAB. We add not just the timing of the light, but also the drift of the signals to the top of the detector, producing a further signal in dark side. And it becomes a very complex experiment. You can see here that it's situated in the Gran Sasso Underground Laboratory in Italy. Professor Galbiati is a professor at Princeton, but also at the Gran Sasso Scientific Institute there in Italy. And the central element in this experiment is actually argon that comes from underground, because argon in the atmosphere has had a radioactive component produced by those same cosmic rays. Cristiano and colleagues from Princeton and elsewhere have developed a site in Colorado where it's possible to extract about 90 tons a year. The equipment has just been shipped to the US from Italy to start doing that. And it will then be shipped across the Atlantic to Sardinia, where it will be purified in this enormous column the size of the Eiffel Tower, which is in an abandoned coal mine. And that also has the capacity to reduce the argon-39 even further in smaller quantities, on the order of a ton rather than the 100 tons we're trying to deal with. Okay, so I was supposed to have no equations and not too many figures. This is the one figure I'd like to try to explain a little bit so you can see what the potential here is. On the vertical axis is the probability of a dark matter particle hitting and interacting with a nucleus. It's a very small probability. The solid lines on this graph show you what has been demonstrated already as being no interaction of the dark matter with ordinary matter. The best of them right now is the data from the LZ project. Dashed lines are projected future projects, which include LZ and Xenon Anton that are in progress now. DarkSide 20K that we're building, and in about 3 years' time we'll have in action. And then finally the Argo experiment, which will go all the way down to what we have been calling the neutrino floor or the neutrino fog, which is where, ironically for me, it used to use neutrinos as a signal. The neutrinos will be a background that we can't get rid of by just going deeper. The potential for this filtering equipment in Sardinia to enable us to work on the far left of the figure with what's called DarkSide low mass. It's a smaller detector designed to get down into that region. There are theoretical predictions for what's called supersymmetry, for the possibility that there would be a particle that has all the qualities you need to be a dark matter particle in this region. But as experimentalists, we're simply pushing as far as we can go into the unknown for things that are very important in terms of our understanding of the world. Again, DarkSide 20K has substantial contributions from AstroCeNT, also from Jagiellonian University in terms of radioactivity control. You can see them here. The contributions are very important in terms of the design of the experiment, and now in terms of supplying the materials to do the job for which they have been designed. We developed brand new light sensing equipment, which is capable of being packaged up to 20 square meters of use in a low radioactivity environment. Also of value for medical applications. And this is something, again, that AstroCeNT scientists and engineers are working on, and that is the development of a new type of positron emission tomography scanner, coming back then to that topic I mentioned earlier on, which will have much better resolution and sensitivity than the ones that are in use these days. The use of argon-xenon mixture for the production of the light and the use of these silicon photomultipliers that I just showed you for its detection results in the parameters that have been simulated here at AstroCeNT, in fact, of this device, which shows you that the sensitivity is significantly higher than other approaches to doing this. And as a result, it may result in positron emission tomography being able to be extended to young people, younger and younger patients, because the amount of radioactivity that you now have to inject is regarded as itself perhaps a risk for younger patients. But if you can reduce that amount that you need to use because your sensitivity is better, then you can get to those younger patients. So it's a prime example. And then secondly, just another example of the way in which basic scientists can also be applied scientists. We partnered with AstroCeNT in the development very quickly, actually, starting in March of 2020, when the real worry for COVID was that you have not only a highly transmissive virus, but also a highly dangerous virus, a highly severe virus in terms of its respiratory problems. It looked in the first phase of COVID that you really needed a lot of ventilators that weren't in existence, and the Canadian government therefore contracted with two or three groups. And we were ready because of being able to adapt our approaches from AstroCeNT to a new unit. We worked internationally. We were working from here to Vancouver, Canada. That's 9 hours time zone. At one point, we were testing some things in Europe and then sending them to Canada, or we had the same thing in Canada. We would let the test in Europe suggest what needed to be tested in Canada. They then worked through the rest of the day, and we took advantage of the time zones, and also Zoom. You may remember that the World Wide Web was invented by a particle physicist at CERN to enable people to communicate. Well, we were really using it in this particular case. In any case, we were able to deliver 7,000 ventilators in a contract with the Canadian government, and they are in stockpile there. Let's hope that the future mutations are continuing to be like the Omicron mutation, where we have high transmissivity but low severity. If we find a mutation where it's the high in both cases, we're going to need ventilators again in the future. So it is an example of how basic scientists can, with strong motivation, pivot to doing applied physics. So I probably talked longer than I was supposed to, but I'm perhaps over-enthusiastic about the topics. This is just a summary of the sort of things I've said. We can do great things in understanding how our universe has evolved. It's an existential question. It's where did we come from? It's how has our world developed? It's fascinating from that point of view. But it also has potentially strong spin-offs, not only in the equipment. It turns out that you have to work with the most advanced equipment in order to do it, but also we've discovered that, and we did surveys of our students, graduate students and postdocs who worked on snow. 75% of them are not in academic, they're not faculty members. They're working in industry, everything from JP Morgan to medical research to a wide variety of other things. And they are regarded as being high-value employees because what they've learned in studying basic science is evidence-based decision-making. You can't get by in science if you try to come up with a conclusion that isn't based on evidence. And that's something that's of great value in everything, from industry. I'm just debating whether I'm going to include government in the list, but maybe I will. It's valuable everywhere, I think, in terms of decision making. So thank you very much.
Thank you all so much, and you've not gone over time. As you know, it's so fascinating. We could just listen for it forever, do it forever. Our time is running. We know that. So thanks for now, and let's thank Professor McDonald again, and welcome to the stage, Professor Barry Barish. Barry, let me introduce you first. So perhaps you can pause for a second. He's a man, like the previous speaker, that does not introduction. He's an icon. He's at least within our community. But since it's the first time he's coming to AstroCeNT, let me just introduce him. Barry Barish is the Ronald and Maxine Linde Professor of Physics Emeritus at Caltech and Distinguished Professor of Physics at the University of California at Riverside in the United States. He's a former director of the experiment called Laser Interferometry Gravitational Wave Observatory, which stands for LIGO. LIGO is the experiment that discovered gravitational waves. On the 14th of September 2019, LIGO made the first ever observation of gravitational waves, confirming a major prediction of the general theory of relativity that was formulated by Albert Einstein in 2015. And it opened up this way a new way to observe the cosmos. Professor Barish was born in Omaha, Nebraska. He received his bachelor's degree in physics in 57 and PhD at experimental particle physics in 62, both from the University of California at Berkeley. In 63, he joined Caltech as a research fellow, became a assistant professor and associate professor, professor of physics in 72, and was named a Ronald and Maxine Linde Professor of Physics in 91. Earlier in his career, Professor Barish developed the first high-energy neutrino beam experiment at Fermilab, a leading US laboratory in physics. Following the neutrino experiment, Professor Barish was the leader of a large international collaboration that performed the search for magnetic monopoles, MACRO, in the laboratory of Gran Sasso on the mountains in Italy, Gran Sasso Mountain in Italy. Professor Barish was also a co-leader of the design effort for a gas electron multiplier detector, one of the two large detectors of the superconducting supercollider in Waxahachie, Texas. He was director of the global design effort for the International Linear Collider. From 2003 to 2009, Professor Barish was served as a member of the National Science Board following presidential appointment. He served as co-chair of the Department of Energy High Energy Physics Advisory Panel, HIPAP, subpanel, that developed a long-range plan for the US high energy physics in 2001. Professor Barish is a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and a fellow of the American Association for the Advancement of Science and the American Physical Society, of which he served as president in 2011. He holds honorary doctoral degrees from 5 universities. In 2002, Professor Barish received the Klopstock Teaching Award from the American Association of Physics Teachers. In 2016, the Enrico Fermi Prize from the Italian Physical Society, and the Henry Draper Medal from the National Academy of Sciences. In 2017, along with Kip Thorne and Rainer Weiss, he was awarded the Princess of Asturias Award for technical and scientific achievements from the King of Spain, and the Fudan Zhuangyi Prize in Shanghai, China. In 2017, I'm getting nearly there, but it's a long list, I can see, of achievements. 2017, Professor Barish was awarded the Nobel Prize in Physics, along with Professor Kip Thorne and Rainer Weiss, for the decisive contributions to the LIGO detector and observation of gravitational waves, which was a historical discovery, like the previous one as well of Professor McDonald. Professor Barish took over LIGO leadership back in '94, but he was involved even before in progressing to Caltech proposing to Caltech to build the experimental effort for gravitational wave detection. LIGO construction was funded late in 1994. He has been deeply involved all the way in LIGO design and finally making LIGO work well enough, which took over 10 years to actually detect gravitational waves. I think that's enough. Barry, welcome to the stage.
Well, let me start first by saying it's been an especially wonderful experience for me this week to follow my long-term colleague, Art McDonald, twice. I don't think we've ever been that close on the stage, and to follow him twice in 1 week is rather special. Art and I actually go back a long ways. I don't think it was mentioned, but part of his early career was spent at Caltech, so we both have the Caltech background. And there's one thing that's done, which people don't realize they don't do large-scale experiments by experimenters, and that is that we have other experimenters, either through the agencies or through ourselves, that we bring in to give us advice, to give us criticism, to convince that what we're doing is right on our experiments. And I had the privilege from actually before Art's wonderful neutrino experiment was built in Canada, when it was just being conceived until it was basically a success. And it did go through some difficult periods. We don't usually share that. And so I've been quite close to his science for a long time. And so it's great to be kind of together, even though we're fairly far apart in what we've done through most of our career. In terms of being here, Leszek and I actually met. Maybe we knew each other before, met and realized the closeness of our vision of physics, what was it, 2019? In 2019. And we've talked since then about getting together and becoming and so forth, and it's now the realization that I'm here. Why? It's actually a shared vision of what we think is where there's opportunities in physics. I'm going backwards or forwards without realizing it. I'll leave that there. What I'm going to talk about today is really pretty much my vision of a particular way that physics will advance. And you can do physics, important physics, in many different ways, of course. Somebody can have their whole career by developing better and better measurements of something important, or you can go to a wonderful laboratory like CERN and develop things there, or you might see opportunities where things aren't done. And the theme of my talk today isn't just what I've done, but the theme of this place here and why it's been created, and that is that I think very deeply that there's a special opportunity to pursue physics in an area that hasn't been pursued very deeply. And what I will give is what I'll show, I think, are just examples, because it's what we're doing now, of why this is an important area. But we've spent centuries studying astronomy, and we're getting better and better at it. We spent a long time studying fundamental physics now with bigger and better instruments. But there's been much less attention paid to the special areas that maybe fall somewhere in between. They either intellectually or technically, or there's no laboratories that work in those areas. We tend to be very specialized, that work in between. So astroparticle physics is an area that it was mentioned that I look for magnetic monopoles. Well, that isn't that magnetic monopoles are astroparticle physics, but it basically is the same idea, that there's an old problem. It wasn't being attacked in any way that was not the conventional way on accelerators, that was somewhere not fitting into the general areas, and we needed to go deep underground, and so we went to the Gran Sasso to do that. And neutrino physics, as we've just heard, has the opportunity, and the shielding of the ground helps. So this general area in between fields, which is what this picture is supposed to indicate, is, I think, a really opportunistic area. Whether you take a photograph of it now, which we heard a lot about, a big piece of it in the last talk, or you look to the future. I think that, so I show the Venn diagram here with a whole bunch of list of things. I won't go through them one by one, which are areas that have familiarity, but they basically have a significant piece that can be done falling in between astrophysics and astronomy and physics, or I used on here plasma physics and physics. And it's that area in between that we're really trying to explore, what this place is about, what a lot of my career has been about, and actually Art's, although he's concentrated on the particular problem of neutrinos, most of the, not all, but most of the neutrino physics that's been done in recent times overlaps with astronomy and astrophysics. So that's the heart of kind of my message, and I'll kind of give you a little history. So I think, in a sense, we celebrated earlier this week Copernicus, and other than the exact thing that he did, which we all know, I would say it was really the birth of doing science, turning astronomy into a science. There were conjectures before him, but he basically did it scientifically. And then, not so long afterwards, came along Galileo, and of course he used, he didn't invent it, but he used a telescope. That was just the time when good lenses were being made for eyeglasses, and that was an opportunity to put good lenses in telescopes, which had been invented. And of course, he looked at Jupiter, and for the first time saw that there were 4 moons of Jupiter. Now we know there are 93 in that last count. But the 4 moons of Jupiter, which I learned about, basically Galileo saw, and it began what I would call observational astronomy, the first time we did astronomy with an instrument and not just our eyes. And Galileo did that in Jupiter. It had the side effect, of course, that he saw that there were moons and not stars, and that they went around Jupiter, and so that followed what Copernicus had learned as well. Now I'm going to jump to the 20th century. And in the 20th century, we saw a big advance in astronomy. And the big advance in astronomy and spirit is like what I talked about. It was changing what had happened for centuries. And that is doing astronomy with visible light that we look at, but also doing it by looking at the electromagnetic spectrum. If we look at this picture here, which we showed our students as we talk about electromagnetic waves with radio waves on one end, all the way to high energy gamma rays on the other end, clearly the visible spectrum is just this little piece in the middle. So it should be clear that if you want to study the sky and use electromagnetic radiation, there's a tremendous opportunity to explore whatever happens in the universe, which is observable in the universe, by looking at all the different wavelengths. And I think, at least in my biased view, this is one of the most important ways that astronomy has advanced in the last 50 years or 75 years or so, was by realizing that looking at the same things or things that maybe aren't in different, there's just examples, in different wavelengths gives you the ability to have all the different information about it and understand what the phenomena actually are. So that's astronomy. We've seen in astronomy one more step very, very recently. I happened to pick up the New York Times 3 years ago, I think it was, or 4. And on the front page, our then President Trump was not above the fold of the New York Times, which is somehow where he managed to get to be almost every day, but instead was a picture of a black hole. And probably most of you saw that. And that happened because of a very clever experiment that didn't just look, say, at different wavelengths, but it was a combination of technical instruments, very cleverly done. They didn't build anything. They just took information from radio telescopes, 7 of them, that were distributed around the world. You can kind of see it in the globe here. And it's not easy. They weren't built to be done this. The data is recorded in different ways and so forth. But they were good enough to take all this data together and make an instrument that was basically, effectively, a radio telescope the size of the Earth. And that enabled them to image a black hole, and we've all seen this beautiful image. And since then, they've imaged also Sagittarius at the middle of our own galaxy. So they've imaged 2 different black holes. And fortunately for me, because then I can stay on top of it, I serve on their advisory committee. Because I didn't know anything about this, but I gave a lecture to my class on it when I saw it in the New York Times. The guy who runs it heard that I give a lecture on it, assumed I was an expert, which I wasn't, and then asked me if I would serve on their advisory committee. Why do they need one? Because they're ambitious now to not just, and you'll hear about this soon, I hope, and that is not just take a still image of a black hole, but actually take movies. They call it movies. Well, we know movies are a set of stills. They're just one after the other. And so the idea is to add a set of radio telescopes that they will add to this, and adding that, the time between images is short enough so you can study the general relativistic effects, which I won't go through now, but are very exciting to test the general relativistic effects on the surface of a black hole. Of course, we'd love to test what happens inside a black hole, but that we're a ways away from doing. So that brings us to the next step, which we call here astroparticle physics, which I think is the next frontier. A lot of that was talked about in the last one. I'm going to pick on a particular area because it's the area that I'm most involved in personally now. It may or may not be the best area of the future. The name is caught on, but we're just beginning, and that's multi-messenger astronomy. So I'm going to talk about a little bit of it from the point of view of what can be done, what we've done so far, and where it might be going. So first, because we've done it so long, one piece of this problem of multi-messengers is well in hand. That is, we have a lot of instruments we can look at for the electromagnetic part, different wavelengths, different frequencies, looking at different places, and so forth and so on. A second element is gravitational waves, and I'll concentrate on that because that's my thing. But that's obviously completely different. Looking at whatever comes from the universe that gives gravitational signals has a different initiation than what comes electromagnetically, and I'll show you an example. So the second is gravitational waves, and the third is what you just heard about, neutrinos. So we have a hope that as we move forward, we'll be able to study what happens in the universe by seeing three very different elements to untangle what the science is. One is the traditional one, electromagnetic waves, but at all wavelengths, as we've learned to do. Second, gravitational waves, which is a completely different source based on what's happening gravitationally in the object you're looking at. And the last one being neutrinos. We've just gotten to the stage where we've done something with gravitational waves, which I'll show, and something with neutrinos, but just the very, very beginning. And again, being an opportunist, I think this is where the future, or a very good part of the future is. When we talk about astroparticle physics, there's a lot of important facilities that are just coming online, so that we'll see a lot of advance in detections of particles and detections of electromagnetic radiation and cosmic rays as well. I show three of them here. I'm going to concentrate on the fourth one, which is gravitational waves, which is mine in just a minute. The one place where multi-messenger astronomy has been done so far is to look at the very highest energy neutrinos that come from the cosmos. And that is being done in Europe, in the Mediterranean, and also deep under the ice at the South Pole in an experiment which is aptly named IceCube. And that experiment is a string using hot water to drill holes, strings of photomultiplier tubes deep in the ice, deeper than particles will penetrate, so that neutrinos, when they come up, if they interact, give radiation that's detected in these detectors. And they've seen at least one example recently of a blazar giving in the sky at the same location that they saw neutrinos. And it's maybe the first indication with particles of this multi-messenger astronomy that we talk about. The example that I'll give from gravitational waves, unfortunately, didn't have the neutrinos detected. And most of this is because we're not very good yet at detecting neutrinos and gravitational waves sensitively enough, but we have the advantage that we see the whole sky generally. So gravitational waves, I'll do this very briefly because I don't want to talk too long. This is actually the picture of the very first event that we observed in our gravitational wave detector. And what you'll see here, I'll just say in words, and that is on the horizontal axis is time. And the event that we saw, the gravitational event that we saw, took about 0.2 of a second. In 0.2 of a second, it basically distorted time and space, which is what we measure, in such a way that it got bigger, as you see, going from left to right, and narrower. That meant that the signal was getting bigger and the frequency's getting higher when it gets narrower. And that shape is done, the reason there's two on the top, two pictures, is two different detectors, they're called interferometers, that we have that are in two different, 3,000 kilometers apart, one in Hanford, Washington, and one in Louisiana, Livingston, Louisiana. And drawn through is lines that you can barely see. The reason the lines you don't see very well is because they fit the data so well. And those are the lines that come from using Einstein's equations of what happens if two black holes hit each other. So we were able, it's very rare in physics, to see a single observation of a single event and with great confidence know that we, not only that we saw something new, but what it was, because it fit this very complicated theory so incredibly well. The bottom picture is taking the fact that there's two detectors, putting them on top of each other, changing the time just slightly because it depends which one got hit first, and they fall right on top of each other. And so that's just seeing gravitational waves. Just to emphasize that, in our discovery paper, this has always been my favorite picture as an experimentalist. The top right is what I just showed you, to the left and the right are the two data. The second, when you go down, second panel is the calculations of Einstein's general relativity. And you can see it looks like that. And as an experimentalist, what you like to do is actually the third panel, which is what I look at, and what I looked at the first day we got this. And that is subtracting the Einstein's equations with there and should be a signal from the data. And you see just a bunch of wiggles. The bunch of wiggles is the data isn't that great, it's noisy, but you don't see any pattern of anything. So this is actually what an experimentalist does. What you'd expect if we're not really seeing what we think we're seeing, or there's something else happening, or there's background or anything else, is you see some sort of pattern or something. The fact that there's nothing there was one of the most convincing pieces of evidence to me as an experimenter, not necessarily to the reader of our paper, that you see a real signal. So we've observed a lot of these now. We've observed quite a few. And interestingly, with the very first event, and then justified by the next couple of years, when we've now got almost 100 events of black holes merging. These are little pictures of black holes merging, mass in units of the mass of our sun on the left-hand side. They're very heavy. You see them near 30, 40, 50 solar masses. That's the unit. And that was not expected. Astronomers didn't expect that there would be black holes that are so heavy. The lesson is something that's been learned many, many times, and that is in astronomy, when you look with a new tool, you see something new. And we saw something new immediately. Not only do we see gravitational waves, but something new in astronomy. There are much heavier black holes than had been expected, because you expect them to occur, to be born by a star burning up all its fuel and collapsing in a supernova. But heavy stars are hard to be stable. Generally, the universe is made out of hydrogen and helium, and the outside then gets radiated, and heavy stars are hard to be stable, so the prejudice was there wouldn't be heavy stars. Neutron stars are much lighter, and they're shown on the very bottom of this plot. So this is now what we've observed. This is everything up to date. We've been off for 2.5 years due to COVID, and we'll be back on with a better detector by summer of this year. Each of these pictures is two objects that are going around each other. They're in a binary system, and then they merge. So you see two objects and then vertically another one. This shows that there's so many of them above 50 solar masses, which is what I just told you. And on the very bottom, we have a few that are very light. Those turn out to be either neutron stars instead of black holes, or a neutron star and a black hole. And we've seen both if you look at these, and I'm not going to go through them in detail. But the point is, when I go back to my original theme, once we have neutron stars, then we have a situation where they can be observed by astronomers. The black holes, all of them, there's not a single paper that's come out that basically has been published that says they saw a signal from any of our black hole events. But the very first observation of a neutron star event produced a immediate ability to study electromagnetic radiation and gravitational waves at the same time. So this is my picture of what will be done many times over in the future as we develop the ability to do multi-messenger astronomy. The picture on the left is a picture of the top three. The top ones are electromagnetic detectors detecting high energy gamma rays, a satellite called Fermi at the very top. And you can see it wiggles up and down. It's a suppressed zero. And then all of a sudden they see a signal out here on the right. And that's their signal. The gravitational wave one is on the very bottom, and it's a time frequency graph that I'm showing, frequency going up and time going to the right. And what we expect when we see gravitational waves, and I plot it that way and instead of what I showed you before, is the lit up part that you see. And so it comes basically what turns out to be 1.7 seconds before the gamma rays. That's interesting in itself, because what we have, we know, which I won't go through with you, where this event happened. It's 150 million light years from Earth. I stated in light years for a reason. If I take 150 million light years, that's 1.5 10 to the 15 seconds. These are within 1.5 seconds of each other, and so that's an immediate proof that gravitational waves and electromagnetic waves travel at the same speed, which is what Einstein predicted, to 1 part in 10 to the 15, which is pretty impressive. That just comes from just the observation itself. Actually, you expect that the electromagnetic gamma rays are going to come later than the gravitational wave, because the gravitational wave comes from the merger of these two neutron stars, and then it's the nuclear physics after they've merged that creates the high energy gamma rays. So there's going to be some time in between that's expected. So, but this proves something that Einstein said, that you go at the same speed. Fortunately for us, it turns out that the Fermi telescope was pointed in the same direction as this event happened. What's shown on the right is the direction that we measured this came from, the littler stuff that you see, the little lengthy thing. And around it is the image of where the gamma rays came from. I had personal satisfaction in this because I have a lot of friends that never said we would never be able to do multi-messenger astronomy because we, meaning gravitational wave people, would never be able to point well enough. It turns out, of course, that we pointed better than they did in this picture, and that was personally satisfying. But in order to do it, we need quite a few gravitational wave detectors around the world and need to be able to point in the sky to something of the order of tens of square degrees. Otherwise, when we tell electromagnetic instruments where we're looking, we're not really small enough. And as we add to the detectors we have now, we'll be able to do that all over the Earth. Presently, that's done by the LIGO detectors in the US and the Virgo detector in Italy, and that's how we got the measurement here. So let me skip because I'm going fast. This enabled us to then, with confidence, alert the rest of the electromagnetic spectrum, and I think it's the biggest mobilization of observational instruments ever done. I think 2,000 people have counted that 2,000 instruments pointed in this direction in the sky and saw what was there. First, of course, us with gravitational waves, visible light, X-rays, even radio waves, which come later, and neutrinos. Neutrinos, as I said earlier, weren't seen, but we wouldn't expect them to be from this. The detectors just aren't sensitive enough. But this whole picture then was looked at quite a lot. The colored waves come in at different times, as we move out to radio being the last one. And so that whole analysis was being able to be done by the observations done over a period of time. And that fit particular models in color and so forth, as I show here, and it's a model that people call a kilonova model. I won't go through the details of that, but that particular model, for example, explains this, the physics of the merger and the emission of the particles and so forth, which we care about as astronomers or as physicists, but it explains something else, we think, and that is a problem that I remember first hearing when I was a student, and that is, how did the heavy elements get into the Earth? We know, and we've known for a long time, or thought we knew, that we make that the universe is made out of hydrogen and helium. That's not heavy elements. That the heavy elements came from the fact that stars burn, and they burn up their fuel, and they collapse, and they make, they work by the fusion process. Well, fusion makes particles that are heavier, of course, than hydrogen and helium, but it burns out at about iron. So you can make particles elements up to iron with the fusion process, but how do you get past that? Nuclear physicists, as I recall, back in the days I was student even, or maybe sometime after that, used what's called an R process, a particular process in nuclear physics, and that it would come from, it would come from the supernova. Well, now, but we don't know because we've seen one event, likely they actually came from the collision, like we've seen, of neutron stars. Of course, one's in the past. This particular event, if you go through the model, not doing anything, and calculate how much neutrons, how much mass of gold. I mean, obviously the question should appeal to the women in the crowd, or all of us that give our wife gold and platinum are above iron. So if I ask how much gold is made in that collision, just using the calculations that I showed you earlier, it's 100 Earth masses of gold in that one collision. So it seems likely, of course hard to prove on one observation, that neutron star collisions in the past made the heavy elements that are a good part of them that we find in the Earth. So what does the future hold? And I'll end on this. We're just beginning in terms of gravitational waves and being able to detect them. The present detector is probably not the ultimate way to do it, but even in the present detectors, we have a feature, and I'm not criticizing another field when I say this because I come from that field. If we look at the discovery of the Higgs boson, which I think is arguably as important as the discovery of gravitational waves, it happened in 2011. We've seen almost nothing beyond that since 2011. Why? It's not because they're not good at CERN. They're really very good, and it's a wonderful laboratory. But it's a 2% effect on top of a physics background. The background is really a physics process. So the only way to eliminate that background is to do something different. In the case of particle physics, you'd have to build a different kind of accelerator. And in fact, I've worked on it, which is an electron-positron accelerator, in which case it would have a much lower background. So the struggles in trying to really understand this crucially important process, what it is, and whether it follows the simplest ideas, that is the Higgs, which is responsible for creating mass in nature, is limited by the fact that it has a physics background under it. Our discovery was 5 years later, but we've gone a long way since then. I just showed you something we've done, not the discovery that we did to win the Nobel Prize, but something that happened afterwards. So we've made progress, and we're going to make even more as we move on. So what's the reason? The reason is, at the present, and that's why I'm so optimistic, the reason is we're not limited by physics. We're limited by technical things. It's completely a limitation technically. And so that limitation can be electrical noise. It can be the air, the air conditioners in the room. It can be anything that causes the object to have backgrounds and limit how well we are. But they're technical. And of course, we can improve things technically. I can't get rid of physics, which is the problem at CERN. So therefore, we know how to make it better, not in one step, but we take what the easiest target is to improve it each time, And you can see that in the graph here. The slope is basically, this is the different colors are the four coming next run, which will start in a few months. And you can see the slope change as we improve our ability to look further out and be more sensitive, and that'll keep happening over the next decade. We also know how to make the next generation detectors that'll be even more sensitive. So the future of doing this on the side of gravitational waves is only going to get better and better, even in the short term, not 50 years, but in the next 10 or 20 years. So improvements for us are great. There's also, in what we already have, the possibilities there might be really new science. And I'm just going to say that just to say it. We're not wagging this yet. But out of the 100 events we have, several of them don't fit anything that we expect. I show on the left the fact that we have, and they may be just experimental technical problems, we don't know yet, but we have a couple examples of events where the mass of the objects in these binary systems is not consistent with either the mass of a neutron star or a black hole, but somewhere in between. We know you can't be too low in mass and be truly a black hole. Neutron stars are a specific mass. Maybe measurement problems, we don't know. We also have very heavy masses and what's believed to be kind of beyond what can be explained easily. So we have examples. This is 100 and some solar masses, 135 solar masses after the merger. And this is real, it's not an error, which has to affect how we think about things. So this science is just beginning. Everything I've shown so far, and I'll just give one other example and close, but everything I've shown so far is examples of something in space, this binary objects that are coming in, and that's a kind of specialized thing. It just happened to be what we could see first. But I've listed here what are likely to be detections of gravitational waves that you'll hear about or see in the next few years. Depending on whether it happens, we might see a supernova. We can see out as we increase the sensitivity well beyond our own galaxy. If we could see as far as the Virgo cluster, there'd be one a year. So we should be able to see supernova. One that I think will be the most yielding in terms of science is if we can detect not a binary system, but a single spinning neutron star in our own galaxy. And the reason is that that's a periodic source. It goes at some particular frequency, and once we can detect those, it isn't like a transient signal like we've gotten from the merger of two black holes, and then once you don't detect it, it's gone. And so once we find a spinning neutron star that we can study, because we see the signal, we can keep studying it with better instruments and so forth and understand the innards of a neutron star, the physics of a neutron star, and the astronomy and astrophysics that comes with it. And lastly, and that's not in the cards yet, but I think is the most important long-term goal, is to be able to do cosmology, again with another tool than electromagnetic radiation, but to start to be able to do cosmology with gravitational waves, which right now we can't. We don't see far enough out. But the ultimate way to look at the early universe, if you can do it, is with neutrinos. If you could do it, that's very difficult, which aren't limited at 300,000 years like electromagnetic radiation from the Big Bang, but a few seconds. Or better yet, gravitational waves, which really go back to the first instance of the Big Bang. We're a long ways from doing that now, but I think the opportunity is there. So I think this combination of techniques, what we call multi-messenger way of doing science is going to pay off in the next decades. And that's it. Thank you.
All right, so thank you very much, Barry, again. And I don't know what your impression was from the talks. Of course, great science great discoveries, very fundamental science. But to me, what transpires from both talks is also the great enthusiasm that you both have for doing research, for this fantastic in those fantastic achievements that you've made. So thank you very much for your talks. Art, could you please also come here? Time is running fast and is shrinking, but we still would want to the question and answer session is shrinking. But before we get there, we'd like to give you little gifts from us. Dr. Marta Borowiec, Director for Scientific Affairs, and Ms. Julia Hojka, our coordinator, have prepared both for you some special gifts, which are astrolabium that Copernicus used. So there's one for you. Hold on, because it can fall out. And this one as well. So I hope you, as experimenters, will help us figure out how Copernicus did it, actually. Because as a theorist, I couldn't figure out. And one more thing. Here's a great painting of our great painter Matejko, who painted Copernicus. The title of the painting is Copernicus Talking to God, after he's making his third great discovery. So I hope you will like them, both of them. Okay, please take your seats. All right, so the question and answer session will be moderated by Professor Cristiano Galbiati, whom I wanted to introduce, except that he has already been introduced by Art McDonald. So Cristiano, the floor is yours. Please moderate the discussion. I hope there will be questions from the audience. I can, if you have no idea what to ask about, I can suggest some. For example, you can ask, is cosmology the same thing as astrology? Or I've heard that the universe is flat, but the Earth is not flat. Does this mean that the universe perhaps is also not flat? Please take your seats and
So thank you very much again to Art and Barry for two inspiring seminars. Let's look if there are questions from the audience. And while waiting for questions for the audience, just to warm up the room, I would like to start with one quick question to both of you. Now, we are here in Poland. We are very honored to be here. Poland has a very strong tradition of excellence in physics, starting with Madame Curie, Zlotowska, but many Nobel Prizes either in Poland or born in Poland. Looking at a bright future of physics, what are your recommendations for the future of science and engagement in science of this very important country in Europe?
Well, I think the simplest is and the most successful is to become as integrated in the international community that does physics as possible. Everything that I showed and what Art showed is being done by scientists from around the world. Science doesn't have any borders like politics, and we do science best when we do it together, and many of us are doing that now. My particular experiment that I talked about has 21 countries collaborating on that particular experiment, and it wouldn't be what it is without having the contributions from all of those, and it goes two ways. It's what the scientists from a given country take home. In our case, an example might be the lasers. The lasers that we use, the special lasers that we use have been brought to us by an incredibly good group in Adelaide, Australia. But from their standpoint, they learned about all the things that we do that they brought back to Australia. So they were able to contribute to make our experiment better, and at the same time, we're able to bring things back. So I think the simplest thing is to integrate as much as possible into the international efforts in the best science you can do.
Well, I have to echo what Barry had to say. I think the international nature of science is very important, and I mean, in our case, working with the dark matter experiment, dark side 20K, the expertise that the group here in AstroCeNT brings in terms of innovative ideas for how to convert the wavelength of light that is emitted by argon into something that we can actually observe, something that's close to visible light, which is where our light sensors work as well, have been an extremely strong contribution. And the expertise in the Jagiellonian University, I'm probably not pronouncing that right, in terms of the radioactivity in these experiments is recognized worldwide. You have experts here in your country that are very good at a variety of things, and they're things that people respect and need in these international experiments. And I think you can benefit both from contributing to these experiments and also learning from them in terms of bringing technology back to your own country. Barry mentioned his contributions to our experiment, the SNO experiment. Barry was an advisor that we were extremely lucky to have. He's not only experienced, he's wise. And that's why he is on so many advisory committees and gives a tremendous amount of his time to such things. But in this case, from the United States, we got tremendous insight from someone who was experienced. International cooperation is something that you can do. The other thing, however, is take advantage of your natural advantages that already exist. In our case, for the SNO experiment, we had a deep mine. We actually had the heavy water as well for the first experiment. Think seriously about your underground laboratory here. That's something that it looks like has a good potential. And so take advantage of your natural advantages in order to be good at a given thing.
So thank you, Barry. Thank you, Art, for this very important answer. And now I see there are a lot of young people, students and postdocs in the room. Let's solicit some questions from some of the younger members of the audience, starting from this corner.
What advices do you have for the young researchers? How to obtain success and don't waste a passion?
That is an excellent question. Let me go to Barry for this. Yeah, what is the advice that you would like to give for young researchers at the start of their careers on how to optimize the use of their talents? If I understood right.
Well, I mean, there's a lot of answers I could give to that, but the easiest answer for me to give that's the most honest is ask myself what I would do if I were your age now. And I think there's more opportunities now as a scientist for a reason that I'll give than when I started. When I started, physics was ahead of almost anything around it in instrumentation. So that if we needed better instrumentation than existed to do a new project, we had to develop the instrumentation. In today's world, there's a lot of instrumentation or techniques that exist that haven't been applied as well as they might be to physics yet. Not necessarily technical, not necessarily instruments, for example, machine learning, and so I think a clever young person can solve problems that haven't been solved before, experimental ones, by taking advantage of the advanced techniques that exist in the outside world that haven't been applied to physics problems, and that's why they're still physics problems.
Thank you, Barry, for this response. And let's see if there are other questions from the younger members of our audience. Over there.
Hello. So my question is like kind of similar, but I'd like to know that being experimentally, sometimes we face like we expect some results, and after doing a lot of study, maybe we are not getting to that point. So my question is like how we should be like still motivated, and how we should continue our research like to get some achievements, some productive things. That's my question. Thank you.
Well, these large-scale experiments look as though they're large-scale, and you don't make progress unless you have the whole thing happening. In point of fact, they're a series of contributions by a series of smaller groups that are doing very important contributions. I think in the process of participating in such large experiments, you can gain expertise in a certain area of physics that can contribute to the large project. You can feel good about addressing some of the most fundamental questions you can ask in the world today by being part of the larger project. You can also develop your own expertise in the thing you're working on. You can develop expertise in interacting with other people, in understanding how to read what's happening in a situation, to learn how to be nice and collegial to other people, because that's the way in which you make the most progress in these sorts of circumstances. So regard it as a step in your learning. You will move from one area to another area. Make sure when you're an undergraduate, you pay close attention to those very basic subjects that you're learning, because you never know, you always find in the later cases where you're trying to deal with an answer to a problem that it's there in the basic physics you learned. But also be curious about the sort of things that Barry mentioned, the latest technology. Keep up on that. Be curious in both areas is the way to go ahead.
Excellent. We have one more question there.
So I have two questions to Professor Barish. So first one is about, you mentioned only about two black holes merging. Is it possible that there are somewhere 3 black holes orbiting around and merging?
Yeah, of course. You do the simplest thing first. So we have 2 black holes, but we're not even good at that yet. We do 2 black holes as long as they're fairly close together in terms of their masses. If you look closely at my data, we don't have a black hole 10 times heavier than another one. And there's reasons for that. The reasons are we're not very good at it. And we're not very good at it because if you take Einstein's equations, it's very hard to calculate what they should look like when they're very asymmetrical. Similarly, if you had 3 objects, we don't have the calculations to know exactly how to look, so we're limited. It's not that they don't exist, it's that we are limited to looking at the simpler thing.
And I have one more question. You have shown a nice image of the black hole. So could you explain what we exactly see? So why the bottom part around the black in the middle is much more light than at the top?
Yeah, let's talk about that afterwards, because basically it takes a little bit.
Okay, can I have one more question to the first speaker? So the spectrum which you have shown, which you describe with 6 parameters, and and with the equation which you have, you can fit it very well. On the left side of the spectrum, actually the points are distributed quite far from this line which describes it. Can you explain why?
Yeah, in the merger, I think if I understood your question, in the merger, the very first is easiest to calculate, but when you get very close together, then this is where the gravitational fields are the strongest, and you get to what's called strong field gravity, and there we can't calculate it as well. We have to learn how to calculate it. So the real test of gravity that we hope to do in the future is where the fields are the very, very strongest. And there we don't use the calculations for the very end.
Thank you.
Okay, I think we have time now for one last question. Yes.
Hi, thank you so much for this great talk. So my question is actually to both of you from an experimental point of view, that how do you guys actually predict that the experiments which are going to happen in future will have such form of sensitivity? For example, when I see the plots for O4 or O5 runs, which are not yet started, we say that, okay, these plots have very high sensitivity, that's why a high count rate compared to the O1 runs. So the basic question that I wanted to ask is that, is the technology already developed, or is it a calculated gamble that you guys take that the difficulties which we face currently will be solved after maybe a decade or so?
A big question on the creativity and the ability to develop for experiments. Art and then Barry.
So we've been very fortunate as we go forward with this tremendous development in computing technology. And the way in which these large experiments get designed, I'm most familiar with mine, Barry can speak about his, is in simulation of the experiment. Basically, you put all of the physics you can think of that's going to influence both the signal and the background in your experiment, and you simulate with great detail and with very extensive programming, which has been fortunately developed as Moore's law came along, and we've increased our capacity as we went forward. And so those simulations are essential in order to design the experiment in the first place, and then they are also very valuable in extracting the information, because you compare what you observe with what you expect to be signal or what you expect to be background. I just want to make one more comment about what Barry was showing, which for me was quite remarkable in another way, and that is Barry showed calculations of how black hole mergers should behave, how the signal should be obtained from these black hole mergers. It's only about, I guess, 5 to 6 to 10 years prior to the first observations that the calculations had reached a level of sophistication that they could actually put general relativity into this process of black hole merging. I can remember individuals that I was introduced to by Dick Bond in some of the meetings he was running, people like Franz Pretorius, for example, who were struggling at the frontier of theory to try to understand what was happening. He and a number of others were successful, resulting in then a signal that could be compared with what was observed. And that's the sort of combination of theory, simulation, and experiment that results in going ahead if you have really good computing power.
Yeah, just to add to this last statement, we knew what Einstein's equations were, but to calculate it on a computer or to do it in a region that you can't do it analytically, numerically, was something that had to be developed. But then we're still not good at doing it. I mentioned that, for example, if the masses are very different from each other. And that's just an example, or if there are 3 of them. So there's more to do both experimentally and both calculationally. And just to add to your question about how do we know that things work, just to add to what he said, which is simulations. In our case, almost everything is tested at a different scale in laboratories before we put it in. So this coming run, the steepest slope that you saw is a particular addition, something called squeeze light. And that is a technique that's been developed in laboratories, and we've developed in terms of how to apply it to LIGO for a decade. And now we're ready to put it in. So we know with pretty good confidence how it'll work in LIGO, and the simulations of what it'll do then to the response is what you see here, and it's probably pretty close.
So thank you very much to Barry and Art, and thanks for the wonderful audience for the strong participation in this seminar. Leszek, to you for the closing.
Okay, thanks very much again to Barry and Art. And thanks, Cristiano, for chairing this session. Unfortunately, we're being pressed by time because of the other historical event that is taking place in Warsaw today. Apparently, the city center is jammed up, so we'll have to transfer to another location, which we were hoping would take only 15 minutes. It will probably take twice as long as, if not more. Despite that, I feel compelled to mention one person that is not here today. Another great friend, great physicist, and also great friend of AstroCeNT, great supporter of AstroCeNT, like our distinguished guest, Stanisław Katsaniewicz, the director, former late director of astroparticular cosmology, and late director of the European Gravitational Observatory, before he actually died at the end of last November, which was a great loss to the whole community, a great loss to AstroCeNT. He was the chairman of the International Scientific Committee of AstroCeNT and a co-father of AstroCeNT. It was a great loss because he was not only a friend of AstroCeNT, of Poland, of the whole community, he was also my personal friend. So I'm mentioning this because his family requested not to lay flowers on his tomb, but instead to make a collection for a charity of sick children. We started making this collection, and if you're willing to chip into this collection, there will be a person standing downstairs at the exit door. If you want to just drop in something, it would be very much appreciated. We all send in to the charity in Greece. Okay, I think it's time to finish, and let me finish by first. Let me ask the invited guests to please remain here for a photo session, a quick photo session, and let me thank again our distinguished guests and friends of AstroCeNT and Polish science, Art and Barry. Okay. Representatives of the Polish government, ministries, representatives of the embassies, and funding agencies, of course, I should mention them, and everybody else, people that I mentioned at the beginning, the researchers and the students who are here, so the audience. Thanks very much for coming. And last but not least, let me thank my guardian angels, Dr. Marta Borowiec, Marta and Julia, please come forward. They made all the preparation without my intervention, and that's perhaps why it went so smoothly. Thanks very much again, and I hope to see you again soon. Bye.